Log on, tune in, find out. Another good idea from Cambridge.
Professor Helge Kragh. He is Professor of the History of Science and Technology in the Department of Science Studies at Aarhus University in Denmark. He is, or has been President of the European Society of the History of Science, a member of the Royal Danish Academy of Sciences and Letters, the European Academy of Science, the Académie Internationale d'Histoire des Sciences. He is a Knight of the Brooks Order. Highly distinguished, a special research interest in the history of cosmology. Brilliant book. We've got a couple of copies of his book, Cosmology and Controversy, on the bookstall, and a number of other books as well that he's written, including to do with entropy and creation. So it's a tremendous privilege to have you speak now then, Professor Kragh. Thank you.
Thank you so much. Let me start by admitting that it's a little awkward for me to give this talk just after Dominique Lambert's very informative, very rich talk. I'm saying this because there can otherwise to be some overlap between what I'm going to say and what Dominique said. Indeed, several of the slides will be more or less the same. But I'll try to speak about Lemaître science in a somewhat different way, somewhat more informed by a history of science maybe. I would ask you to say about the science-religion connection, because that will, in any case, be covered in considerable depth by other speakers. Well, I like this picture very much. And here we have George, I believe, with his two brothers. Well, in order to understand Lemaître's contribution to science, we have, of course, to understand the background at about 1920. We have to be aware that Einstein's general theory of relativity was quite new. Basically, it was only known outside Germany, of course, after the end of World War I, when Einstein's cosmological theory in 1917 became known among a few specialists, Lemaître being one of them. But one thing is the theoretical scene, another thing is observations, and we shouldn't forget about those either, although they were basically disconnected from theory. Let me point out that about 1920, the question of the redshift of the nebulae came to the forefront of the works of astronomers. Very briefly, a few years before World War I, starting in 1912, Melvin Schleifer at the Lovell Observatory in Arizona discovered the galactic or nebular redshift. Well, to speak the truth, his first redshifts were not red, but blue shifts. But he figured out that these were exceptions, and the more galaxies he studied, the more evident did it become that they exhibit a systematic redshift. From about 1920, several astronomers and physicists speculated whether this redshift phenomenon could be explained theoretically, in terms of relativity maybe, or if there was some kind of systematic relationship between the value of the redshift and the distances as a nebula. Here we have the best data from 1924 collected by a well-known Swedish astronomer at the time, Knut Lundmark. And I think you will agree that one has to have a very good imagination to see a straight line. The main problem was not the determination of the redshifts, but the determination of the distances to the galaxies, about which very little was known. And that, of course, is where Edwin Hubble enters the picture. Famously, he announced on the first day of 1925 that he had discovered a Cepheid variable in the Andromeda that furnished the necessary cosmic scale, and he could establish that, or he could give solid observational evidence that we live in a so-called island universe and not in a Milky Way universe, which ended this so-called great debate, more or less. Not instantly, of course, but certainly by 1927 or so. But it took several more years until the galactic distances, enough data had been collected until Hubble could, in 1929, publish his paper in which he argued from data which were not very good, but that there is indeed a proportionality between what he called the apparent velocity of the galaxies and the distances, the Hubble relation, or as it became known much later, the Hubble law. Now, on the theoretical front, more or less in the same period, there was one piece of work which Lemaître, by all what we know, did not know about, but one might say that he ought to have known about it. It's a bit strange that he didn't, but then he wasn't the only one who didn't. So I have to refer to Alexander Friedman's seminal work in 1922. He followed it up 2 years later. But very briefly, what Friedman discovered was that Einstein's cosmological field equations are much richer than Einstein, or for that matter, Einstein and de Sitter believed. He showed that in the case, well, assuming the cosmological principle to be valid, assuming a homogeneous and isotropic universe, he showed that these tensor equations could be reduced to a set of very simple differential equations, currently known sometimes as the Friedman equations, sometimes under other names, Friedman-Lemaître and Friedman-Lemaître, Robertson-Walker, and so on. And he published this, I mean, it's sort of interesting that Friedman, of course, was Russian. This was a period in which Russia was very much separated from Western Europe for political reasons. But he managed to publish this paper just in the right journal. The Astrophysics, which was at that time a new theory of progressive theoretical physics, specializing in quantum theory and relativity theory and that kind of things. So this paper appeared in the right journal, in the right language at the right time, and nonetheless it was almost completely ignored or misunderstood. As Dominique mentioned, there is no doubt in reality that Lemaître was unaware. It has been suggested that he was, and he, but there's just no documentation for that. But then, as I said, Lemaître was not the only one. We know quite precisely who cited this paper. There were very few citations of it. There were some, but these few citations were not concerned with the cosmological substance of it. The other point, which is necessary to notice, is that although from a mathematical point of view, was a great deal of similarity between this paper and Lemaître's later paper. I mean, the mathematics is almost the same. From a physical point of view, the two papers were entirely different. It's so obvious that Friedman just was not interested in the physics. It's noteworthy, for example, that such key words as galaxy or nebula doesn't appear in that paper. Radiation, energy, matter, these words doesn't appear either. And it's not really correct to say that Lemaître nonsense, that Friedman discovered or predicted the expansion of the universe. I don't think that's fair, because what he did was to point out that from these equations it is possible to derive various models, some of them being expanding, some of them being an oscillatory nature. So he gave the various possibilities, but he didn't express any preference for any of these. And most importantly, he did not connect them at all to the redshift, which he didn't mention either. Although there's reason to believe that he didn't know about these redshifts. So 5 years later, 1927, Lemaître unknowingly duplicated much of this work. And I have to show you, or to say a few words about this paper, because Dominic certainly is correct in emphasizing that this is probably, I mean, this is really one of the most important papers in history of modern cosmology. It's a wonderfully rich paper, but I think it's fair to say that Lemaître published it in the wrong journal. This was not a journal well known to physicists and astronomers at the time, and in fact this paper was even more sorrowfully ignored by then Friedmans. We know that Lemaître sent copies to it to the two most important players in the field, namely to Eddington and to de Sitter. We also know that they didn't respond well. Eddington did some years later, too late, but when he did respond, things began to roll. It's also well known, and I think that we'll hear more about it in this afternoon, that this paper became better known when it was translated in the monthly notices of the Royal Astronomical Society in 1930 on the instigation of Eddington. But for not very good reasons, I think, it was not brought in its full version. And it's especially regrettable that most of this page, including this very rich footnote, was excluded from the translation. So readers reading the monthly notices didn't get the right impression of how closely Lemaître connected his mathematics to observational data. Here we have this discussion of what became known as the Hubble constant or Hubble parameter, for which he obtained a value roughly of the same order of magnitude as Hubble did 2 years later. But we will hear more about that. Also, the title of the scientific paper is important. And it should be pointed out that Lemaître chose this title, a homogeneous universe of a constant mass and decreasing radius, accounting for the radial velocities of the extragalactic nebulae. So this is much more specific. Even in the title, he singles out a particular model, which he believes is the right one for observational reasons. Yes. I think it's reasonable. Let me rephrase it. If one insists that the expansion of the universe has a discoverer, and this is not obvious, and not all discoveries can be attached to a discoverer. But if one insists so, the best author by far would be Lemaître, in the sense that he predicted the expansion and he argued for it empirically. It was definitely not Hubble who discovered, although one can read it in many books and many papers. I would like to refer, if people would like to know more about that, some years ago I wrote together with a Canadian historian of astronomy, Robert Smith, a detailed paper with the title Who Discovered the Expanding Universe, and you can find all the arguments pro and con there. So here we have the first determination or estimation, to use a better expression, of the Hubble constant, a constant which the astronomer Eugenia Trimble once referred to as the incredible shrinking constant. For obvious reasons, well, it's not shrinking anymore, but it did for a long time. And of course, there is a history behind that. I have to say, I have to say a few words, but not very many, about this model because Dominic has already told about it. So I really only want to emphasize once again that there are these two models, or these two theories, the theory in 1927. For historical reasons and for practical reasons, this is often referred to as the Lemaître-Eddington model, sometimes Eddington-Lemaître, but who cares? And then there is the Lemaître model. The Lemaître model should be reserved to the 1931 Big Bang model. The reason why it's called, often known as the Lemaître-Eddington model, apart from distinguishing for this model, is that when Lemaître and Teixeira rediscovered his work in 1930, Lemaître nonsense, Eddington right away started working on it, and not only Eddington himself, but also some of the students, McCrae, McVitie, and others. Of course, 4 years later, we have the other similar contribution of Lemaître, and the reason why we are rather here. We already have seen what the essence of this so-called primeval atom hypothesis was. Perhaps I should point out, although Dominic already did, that it's a Big Bang model. Surely it's a physical Big Bang model, but it's not a model which starts in a singularity. It starts actually in a rather big thing. A highly compressed and maximally compressed physical thing of the order of the size of the solar system, something like that. Whether this is a big or small thing, leaves to you. And this thing he described as a primeval atom, a l'atome primitif. One should be aware that he didn't really, this is metaphorical description. He needed to use metaphors, and he chose the atom as a metaphor. And really, in some sense, in the original meaning of an atom, as something totally primitive, undifferentiated, the meaning of the atom, as in the ancient times of Democritus and the Greek atomists, rather than in the modern sense. He might as well have called it the primeval atomic nucleus hypothesis, because of course he didn't conceive this early universe as an atom with a nucleus and extra nuclear electrons. These electrons were absorbed or swallowed by this enormous atomic nucleus. And one should be aware that we are in 1931, and that people at that time knew very little about the atomic nucleus. It was basically a terra incognita. People thought, all physicists thought, including Lemaître, that an atomic nucleus consists of protons and electrons. This is 1 or 2 years before the discovery of the neutron. So given the lack of knowledge of the atomic nucleus, what Lemaître really wanted to emphasize was that it was a material beginning in some unknown but extremely compact state of matter. An atomic nucleus at that time was the most high-density object one could imagine. 10 to the power of 15 gram per cube centimeter. Today we can imagine much more dense objects, but when he published this suggestion in his famous letter in Nature, and we have already heard about that, but let me just compliment that we know from his original typewritten manuscript that he thought of including in this letter a direct reference to God. And we also know that this actually, apparently he deleted it, most likely, I guess, because they didn't want this idea of hypothesis to be mixed up in people's mind with religious reasons. There is another small and not uninteresting point in this most remarkable letter. I mean, less than half a page in Nature. And we have already seen that, but I want to repeat this really wonderful and most poetic and most meaningful end of it, in which he likens the initial quantum to a phonograph. What he's saying is that how can such an undifferentiated simple thing result in such a rich and colorful world that we observe? Something must be created. How can we explain the contingencies of the world? We certainly cannot do it if we subscribe to determinism. But then we don't have to subscribe to determinism, as he says, because we have quantum mechanics, which is acausal and and non-deterministic. We have Heisenberg's principle of uncertainty and so forth. So the whole story of the world need not have been written down in the first quantum like a song on the disc of a phonograph. The whole matter of the world must have been present at the beginning, but the story it has to tell may be written step by step. That's very nicely put. I also want to point out this small point that people reading this letter probably would have no idea who the author was. He's just signing it as Lemaître. He's not signing as professor of the Institute of Astrophysics or whatever, but as a private person. And again, there must have been reasons for that. So that, of course, is the birth of the Big Bang idea in a certain sense, at least. It was not a success from the ordinary sociological point of view. On the other hand, Big Bang models of a kind, at least, begin to start not only with Lemaître's model in 1931, but also with other models. So we have a strange phenomenon in the early 1930s that certain very prominent people in the field proposes cosmological models which we would call Big Bang models, but they probably would not. So let me refer to none other than Albert Einstein, who in 1931, in a little known paper, but this was at about the same time as Lemaître's letter in Nature, and completely unconnected to it. But Einstein, in this paper presented to the Prussian Academy of Science, proposes this kind of model, a so-called cyclical model with a Big Bang and a big crunch, of course not his names. But he says that if there is enough matter in the universe, that is what would happen. This is the paper in which Einstein's officially, so to speak, get rid of the cosmological constant. It is a Big Bang model. But there's absolutely no indication that Einstein thought of it in that way. There's not a word about the beginning of the universe. Then the next year, we have the much more important so-called Einstein-Cassini model, which in the 1940s, 50s, and 60s was probably the most quoted and the most credible cosmological model. In this important paper, which we have here, this parsimonious universe with a flat space, no cosmological constant, no pressure, but it continues to expand forever at a constant rate, and this most definitely is a Big Bang model. And it's very easy to write down the way in which the curvature depends on the time. It's very easy to calculate the age of the universe, which is 2/3 times the Hubble constant. Einstein and Cassini did not do that. One will look in vain for it. There's no reference or even indication that this was a model including something of a beginning of the universe. So people tried hard to ignore Lemaître's suggestion that there was indeed a beginning, but this was a concept which was unwelcome. And there's many indications of that. For instance, in 1933, one of the top people in relativity and cosmology, H.P. Robertson at Princeton, wrote a most influential review article in the Reviews of Modern Physics. That was the kind of article which charted the field and in which people interested in it looked for information and for references. In this rich list of references, one will look in vain for Lemaître. He does indicate, without mentioning Lemaître by name, that there is a possibility that the universe started in some abrupt way and that we can assign the meaning of beginning to it, but this he doesn't like at all. He's much more in favor of the Lemaître Eddington model. So if one wants to find information of how Lemaître's model was received, one should not only look in the scientific journals or in the scientific books. One should look at newspapers, and one should look at in the popular journals as well, at least. And there one gets a fairly different picture, because his model apparently was quite popular, at least for a period. We have already seen some clips from newspapers, and I want to point out to this very nice and very interesting article in a popular science monthly. And it's from the end of 1932, which means that it's a very early reference. In fact, it's one of the earliest papers which deals in considerable detail, of course purely qualitatively, with Lemaître's theory, written by a noted American astronomer from Harvard. And he gives a rather detailed account of Lemaître's theory, whether this headline is his own or the editor of the journal, but apparently the editor couldn't resist the temptation to speak about the creation of the universe, and as we know, Lemaître never did that, and he had good reasons not to use that word. But here we have it, and it's even more interesting because in this article he makes a direct connection between the primeval atom and then what happened in nuclear or early elementary particle physics at the time. Notice here we have Ernest Lawrence's, the first generation of the cyclotron, the big machine which could split atoms. And so he's sort of suggesting that we can get knowledge, we can get information about the early universe by studying in the laboratory nuclear processes. So this is the germ of what later on became known as astroparticle physics, the inner space, outer space connection, which is as a flourishing field of research today. Dominic paid some attention to the cosmic rays and to Lemaître's idea that the cosmic rays are the fossils of the original explosion. I'll just say a few more things about that, because after 1931, well, after he published this letter in Nature, which is not a scientific article at all. It's a letter, sort of poetic and appetized, I don't know how to describe it, it has nothing to do with the scientific article. But later the same year, he participated in a conference in London, where the meeting of the British Association for the Advancement of Science took place. He was a member of a group discussing these things. And also, at about the same time, he wrote a paper in a Belgian journal of some prominence, the Question Scientifique. And in this paper, he outlined in more detail, including some of the mathematics, the Lemaître model. But of course, he was very well aware of the difficulties of answering the simple question, Monsieur Lemaître, why should we believe in your theory? Can you give any evidence for it? And he thought that he could, namely the cosmic rays. I'd like to point out, in addition to what Dominique already mentioned, that the cosmic rays, were actually discovered about 1912, 1913, but it took a very long time until people really knew something about these rays. The very term cosmic rays was coined by Millikan in 1925, and at about 1930 there was a controversy or a debate between two different views regarding the nature and the origin of these cosmic rays. One was associated with Millikan, that is the idea that the rays are high-energy photons. The other, the rival theory, was mainly advocated by Arthur Compton effect fame, who argued that the particles were deviating in the magnetic field of the Earth, hence had to be charged. So he thought that these rays were principally made up of protons and alpha particles, electrons, things like that. And there was for a couple of years a great deal of uncertainty. Of course, Lemaître and his collaborator, this Mexican series, Manuel Balata, believed that the Compton theory was the right one. He wanted to believe it, of course, because in that case he could see the cosmic rays, the protons, the alpha particles, at the decay products of the original explosion. And that was, this idea, as Dominique already had said, was in principle a very good idea. And it was of scientific validity. Unfortunately, it was wrong. People didn't know that at that time. It took a very long time until the nature and origin of the cosmic rays were probably understood, and it's still an area which is not completely understood. But the cosmic rays, contrary, of course, to the microwave background radiation, are not of cosmological origin. I will skip over this because, as Dominique already has emphasized, this pioneering work which Lemaître and Balata made with this not only state-of-the-art computer. It was a mechanical computer originally, something of a monster, but it was used with these very intricate calculations, and as Dominique mentioned, this was very much, apart from the connection to the Big Bang theory, it was also very much to the heart of Lemaître, because he simply likes calculation problems. But let me say a few more words about the reception, or one might even say the non-reception of the primeval atom idea. Basically, this idea was in the scientific circles either ignored or criticized, in some cases even ridiculed. I have just a couple of examples. One of them is a bit more interesting than the others because that is the Bishop Barnes, a most remarkable person in this book, which some of you undoubtedly know, Scientific Theory and Religion, is an extremely interesting and remarkable book. As someone once said, this is probably the only work on theology which is filled by page after page of heavy tensor equations. Barnes actually was a mathematician. He taught mathematics for a period of time in Cambridge, and then he entered this. And he was very well at home in Einsteinian cosmology. But he had these ideas. He characterized this idea as a clever Schrödinger. One shouldn't take it as for more than that. is John Plaskett, a British-Canadian observational astronomer. He was director of the Dominion Observatory near Ottawa, a man of some prominence in the Astronomical Society, which he flatly characterizes as the widest speculation of all, an example of speculation run that without a shred of evidence to support it. My last example is from one of the classics of early cosmology, a book entitled Relativity, Thermodynamics, and Cosmology. One can still buy it as a Dover edition, for that matter. And I think it's probably the first textbook in relativity cosmology. Tolman was a very important and influential figure, originally a chemical physicist. A physicist, he was at Caltech at that time, and a big specialist in thermodynamics and application to cosmology. And well, we have him here. This is Tolman. This is Einstein, of course, Elsa. This is Lars Meyer, one of Einstein's collaborators at the time, the fifth person, I do not know who is. But Tolman, he warns that although there are models which formally starts in a singular state, and we should not take these models as proof that this is how the real or actual world is. Which is, of course, correct. And then, by the way, Lemaître's model was start in a singular state. Yeah, I would like to say a few words about the cosmological constant, a few more words than we have already heard. Here is another most interesting paper by Lemaître, and another paper which was more or less ignored for a very long time. And that is a paper, 1934, in which he says, as the very first one, I believe, that the cosmological constant should be understood physically as the vacuum energy corresponding to a vacuum pressure, a negative vacuum pressure, and he gives this translation between the energy density of vacuum and the cosmological constant. Now that, as I said, didn't really create much interest at the time. Lemaître, of course, was a big fan of the cosmological constant from the very beginning to the very end of his days. That, by the way, was also the case with Eddington, although for other reasons. Einstein changed his mind. Already in 1919, Einstein wanted to get rid of this constant, which he disliked for aesthetical reasons. But he could only do so in 1930, 31. And there is, later, we have a correspondence between Einstein and Lemaître. And this is a correspondence relating to the Einstein-Festschrift, which was published in 1949 in the Philosopher Scientist series, in which Lemaître wrote a contribution. And so Einstein, he says that he can't believe that such an obvious thing should be realized in nature. It's just awkward. Well, of course, these kind of aesthetical criteria are not necessarily convincing to people who have other standards. And as far as Lemaître thought, he liked it because it gave the theory a greater deal of flexibility. And he thought that Einstein's invention of it was a happy accident. So Lemaître made these very important contributions to the early history of cosmological constant. Here I have listed some of the highlights in this development. Of course, it's standard and correct to say that it was invented by Einstein in 1917, but I would like to point out that there was a kind of classical predecessor that one can find the cosmological constant even with the same Greek symbol. in a work of the late 19th century within a purely Newtonian context, in which one of the important astronomers of the days, Hugo von Seeliger, explores an infinite stellar Newtonian universe and shows that such a universe can only be stable if one changes Newton's law of gravitation at very large distances, and that's where the lambda comes in. This is essentially the same function which lambda has in relativity theory. Then Lemaître's contribution, but Lemaître, although he made the connection very clearly to the actual energy and pressure, he did not make any connection to quantum mechanics. Quantum field theory, that comes much later. As far as I know, first with Jakob Sadowitz in the late 1960s, then with other persons, and then this area became very important, developed and examined by a number of physicists and cosmologists. In 1987, Weinberg wrote a famous paper in which he examined it, and he pointed out, as other people have done, that there is this cosmological constant problem, this huge difference between the observed value, and then the one predicted from quantum theory. Whether this is a solved problem or still one of the unsolved problems, I guess there are some disagreement between people concerning that, because that's where the atomic principle comes in. I would like to end with just two slides referring to the late Lemaître, so to speak. And it is true that Lemaître's interest in cosmology faded, I think one can say, in the 40s and 50s. He had other things to do, and he disliked somehow the new development with Gamow and his physical Big Bang. He even more disliked, for natural reasons, the steady-state theory of the 1950s. And perhaps, well, so he really hadn't, he was not a key player in that area. At the Solvay Conference of 1958, which is, I mean, at that time the Solvay conferences didn't have the same status as they had in the 1920s and 30s, because there were so many other conferences. But still, this one is rather remarkable. It's the first conference devoted to cosmology. Actually, it's one of the first international conferences ever devoted to cosmology. And at that time, nobody could tell for sure whether the future of cosmology belonged to evolutionary relativistic theory or to steady-state theory. So here we have Fred Hoyle, we have Bundy, and Gould, and Hal McRae, all four leading steady-staters. Gamow was not invited. The only one representing a Big Bang was Lemaître. I would like to emphasize that at that time, during the 1950s, all the way up to 1964, 65, the Big Bang theory was dead, completely dead. So it had to be reinvented. And at this occasion, Lemaître, he gave a very interesting and beautiful account of this theory, but also it was a kind of déjà vu because there was nothing new in it. It was basically the same thing he had said in the 1930s. The last thing I want to mention is that sometimes one can read that Lemaître was in favor of the so-called cyclic or pulsating universe, or what sometimes is referred to for good reasons as the Phoenix universe, referring to the fable of the magical bird Phoenix. But that is not the case as far as I know. It is true that he referred to it, and he was one of the first to use this term. Where is that? That's 33, and he said that it has an indisputable charm. But that doesn't mean that he was in favor of it, of course. It's just a charming picture of a possible universe that one might imagine. And later on, at the start of the conference, he distances themselves from it, which makes sense to us, because at least historically and traditionally, at least the eternally cyclic universe has always been associated with materialism and with atheism. So it would be somewhat strange if a person like Lemaître subscribed to this kind of model. Thank you.
Thank you very much indeed, Professor Kragh. So again, we've got some few minutes for questions. Yes.
You mentioned in 1950s, 1960s, the steady state universe was the dominant
No, he didn't say that.
theory that Big Bang was sort of out of favor. But I think maybe that was too pessimistic. When I was at Princeton at the time, certainly there was much more talk of oscillating universes, expanding universes. There, at least, the steady state was not too enthusiastic, not accepted with much enthusiasm.
Yes, but it's quite true that the support of steady state was very technical. It was somehow it was a very British theory. Very few persons outside the UK supported it. But on the other hand, there were, this controversy was a controversy between steady state theory and then relativistic evolution theories, not theories with a Big Bang. I have covered this, and I have found one paper between 1953 and 1964. Apparently, one paper only was written on Big Bang theory. So that comes pretty close to this as far as I. Thank you.
But can I just ask for clarification about who you think should get the credit for the cyclic model? Because I think the earliest reference you gave was to the Einstein model of 1931. Lemaître is 1933, but it's often associated with Tolman, who was 1934. So who actually was the first person really to propose the cyclic model?
To propose what model?
The cyclic model.
That one. Well, that would, to my mind, I have written a paper on that in some detail, and the honor or credit should go to Friedman in 1922, I think. No doubt about it.
So he explicitly talks of cyclic model.
Oh yes, he did.
Yeah.
As a possibility, of course. Friedman too was charmed of it.
Don Page, yeah. No, I was just curious on this last point. In Lemaître's paper, did he say anything about the problem of entropy? These recycling things, of course, as Tolman pointed out, there was this problem of the entropy.
Yes.
So was that a problem for him with this, or do you think it was more theological?
It was absolutely a problem. Friedman didn't mention it, but in the 1930s, Tolman goes in great detail with arguing that is not necessarily a problem. And that is sort of indicated that the radius of these increases all the time. And there's a lot of discussion on that, but the entropy problem was recognized to be a problem for these kind of models for a very long time. Still, I guess. I would like to mention, it's probably unknown to you, but this person here is was a Dutch astronomer, Herman Sansler. He was one of the big advocates. He really believed, in part for spiritual reasons, really, in this ever-cyclic model.
But so did Lemaître himself refer to entropy at all, or did he give any more reasons why he didn't like the model?
Yes, I think he did.
Yes. He gave some arguments coming from a certain principle of thermodynamic data.
Okay.
In fact, you cannot produce large-scale structure from this entropic state if we have an infinite past, for example.
Yeah.
He gave such arguments.
Okay.
Yes, Simon.
Yeah, just wanted to point out that when discussing and writing about the status of cosmological theory in the 1920s, 30s, and 40s, it's important to bear in mind that using the expression Big Bang has a small danger of being anachronistic, because the expression is first used on the 26th of March, 1949, in a radio broadcast, and it first appears in print in the Listener magazine. Hoyle used it as a very graphic way on radio of describing an expanding universe, which of course, as we all know, he disagreed with. On the reception of the steady state theory, I think we can probably agree that hardly any theorists anywhere took it sufficiently seriously that they wanted to investigate it. And the reason why it was so popular as an English phenomenon, which I think you said, is because Fred Hoyle was such a superb self-publicist. In 1951, his royalties from his book, The Nature of the Universe, which puts these ideas forward, his royalty income was 6 times his university salary. And the top rate of income tax for the Brits in this audience was 18 shillings and sixpence.
Thank you, Simon. Yes.
80%. So, you mentioned Lemaître's sort of unenthusiasm for the work of Gamow and so forth. Do you have any information on the reason for that?
Well, I think it was, somehow it was a matter of his personality and his fundamental likes and dislikes. Not that he disliked the theory, but his kind of physics was very much Einstein's. His ideas of physics, that was very much general relativity. The kind of nuclear physics and particle physics, with all their particles which smell too much of botany, as some people said at the time, just didn't appeal to him. And we know that when he was old in the 50s, maybe early 60s, that it must have been Goddard who asked him, suggested that he should communicate with Gamow, but that he.
There may have been a personality clash as well, possibly.
I think so.
That's a rather different, yes, in some ways. In many ways.
One of Gamow's problems was his heavy drinking.
Well, I hesitated to say that.
Yeah.
Yeah.
You mentioned, let's go back to the 1930s, and you mentioned the analogy or the metaphor that Lemaître uses with this atom that articles in something monthly. And I was wondering, something that you published a lot about, not only the atom, but the prototype mentality that there is in the 1920s and 1930s of trying to make matter made of one thing. So I wonder if you have any thoughts about not just the word atom, of the metaphor of atom, but the Primeval atom in George Lemaître. So if that is something about everything made of one thing, kind of stuff in George Lemaître.
I cannot really say, but at least it's my impression that when he speaks about this primitive atom, he's thinking of something which exists, but it sort of semi-exists, because it has no physical properties whatsoever. And yet it is different from nothingness. I'm sure you can say. You can say something more sensible.
Yes, that's a question.
It was a way to speak of the unspeakable.
Go on.
I think one question, because I'm fascinated by how Friedman's paper was ignored, even though it was in such a prominent journal. And I sometimes wonder whether, even if Lemaître had published his paper in a more prominent journal, would it have been ignored anyway?
Yes. I mean, people have, of course, looked at the citations, but they also looked in the abstract journals. where the two come are brief abstract. So we know, for instance, if I remember correctly, that Lemaître's paper appeared in the Astronomische Nachrichten in their abstract, but just with the title. Very uninformative, and that Friedman's paper was abstracted very briefly in some of the German abstract journals under general relativity, under astronomy.
Thank you. Well, we have just about reached 11 o'clock, so I think we're in good time, and I think we should offer Professor Kragh a big round of applause.